to find out this middle hyperplane. The middle hyperplane has the property that it is parallel to these particular the dotted planes, which are themselves also parallel. So that the middle hyperplane is uh, away from these two particular parallel planes, as much as possible. They are possible. So that all the subtle points are completely on one side, and all the the class one negative, the square points are on the other side. And when we do that, the problem is basically find this middle plane, that is W transpose H plus B. This is the plane which I am interested. Assuming that this is the equation, then what actually we are finding is that the distance between the parallel planes as m, which is equal to 2 upon the length of the vector W, and this is the the distance between the parallel ones. This we wanted to be as far away from this distance we wanted to maximize it. What is the condition? The condition is that all these the subtle points, they are completely lying on the positive side. Not only the positive side, they have to be greater than or equal to 1. That means that they have to be away from the parallel plane, the other side of the parallel plane. And similarly for the negative points, so the negative points are such that they have to be away from the W transpose X plus C equal to -1 plane, actually. Which means W transpose X plus B must be because these are all negative side, so less than or equals to minus of 1. So this particular property is this is how we normally formulate. So our problem is basically maximizing the distance between the two parallel planes, which is 2 upon norm of W, so that for with positive class of points, W transpose X plus B has to be on the away from the parallel equals to 1 parallel plane on that particular side. And negative points are in such a way that they must be away from, on the negative side they must be away from the the parallel plane W transpose X plus B equals to 1, which means less than or equal to -1. So this is what the problem is formulated. But the question is that this particular problem mathematically is like difficult to solve, because first thing is that already we have seen that earlier that the length of the vector W is nothing but square root of W1 square plus W2 etc. The square root is difficult to solve. First of all, that is one problem. Another thing is that it is appearing in the denominator of the 2 upon norm of W. This denominator distance is again the it's difficult to handle for solving. So what actually we will do that we will just as a equivalent problem. What is the meaning of equivalent problem? Equivalent problem is that the first problem, and from that I am going to come out with another problem. The problem is such that solving the first problem is same as solving the second problem. Both gives me the same solution. So that is what is the meaning of that. Right? Okay. So from this particular problem, the maximization problem, now I am going to go for the minimization problem, where the denominator which which is coming the length square root of that, that is norm of W, which is the distance the length of the vector W vector. So this particular one I wanted to instead of appearing the denominator, I want to take it to the numerator. So this is possible by means of a minimization problem. So the problem is that I am taking it as I take it to the numerator first. So I have minimize, the problem is equivalent to minimize the length of the vector that is norm of W by 2, subject to the constraint is saying, as we have stated in the previous slide, that is for yi plus 1 point, W transpose xi plus b is greater than equals to 1. This is equivalent to saying that you multiply both sides by yi, no inequality is changed, and for W yi is equal to -1, W transpose xy plus b less than equal to -1 is multiply both yi on both sides. Then the left hand side is yi times of W transpose xy plus b. Now instead of less than equals to, now you will have greater than equals to 1. And since yi value is -1, so -1 into -1 will be +1, and therefore you are getting yi times of W transpose x plus b is greater than equals to 1 is going to be, it should be satisfied. So our problem is maximization of 2 upon length of W subject to yi times W transpose xi plus b greater than equals to 1 is the problem. And now, as I already stated that the So the constraint is, okay, now, we have clubbed the, the two positive points, positive class points and the negative class points. Instead of having two type of constraints, we have brought them into one type of, the constraints. And but what about, the maximization problem? We are taking into the minimization problem. The minimization is such that, I have taken a square also, where the length of the vector which was appearing in the earlier time in the denominator, now it has taken into the numerator, so the problem becomes a minimization problem. Not only that, I am taking the square of it. Square, I am taking it just as I stated earlier, to remove the square root which is going to appear in the definition of the length of the vector. Norm of w, which is nothing but the length of the vector, is equal to square root of, assuming that w vector has components w1 etc. wn, the norm of w vector is equal to the square root of w1 square plus w2 square plus etc. wn square. So that, now square root is also, gone. So now you can see that the problem is basically it's a minimization problem, okay? And constraints are, linear constraints. Since norm of w square is nothing but w1 square plus w2 square plus etc. wn square. So which means that, it's basically it's a quadratic programming problem. And now the question is that once I have, now brought my, the initial starting, the problem into an operation problem, with our what is the things which we have considered, and then, we have arrived at the operation problem now. So solving is the usual optimization technique. So you go normally for the dual problem, and how you do it. You construct the Lagrangian multiplier actually function. You construct by introducing Lagrangian multiplier. You construct, the Lagrangian function. So I am introducing the Lagrangian multipliers alpha 1, alpha 2, etc. Since, I have m number of input vectors, I am assuming it at the beginning, for the classification problem. And since I have m number of constraints, m number of input points, you can see that the problem has m number of constraints, because, you have yi, xi is coming, where I is varying from first input data point, second input data points, and etc. m input point, because we are assuming that the total number of input points are m. So this is a minimization problem with m number of constraints. So when I go to the dual problem, the dual problem will have now m, everything I will be writing. The dual problem, we are going to write it in terms of the dual variables or Lagrangian, that is by introducing Lagrangian multipliers, we are going to construct it. And I am going to introduce m number of things, the constraints, the primal problem, that is the first starting problem, minimization problem. It has m number of constraints, and therefore, when I have to introduce m number of Lagrangian multipliers, and I can find out, Lagrangian function. I can define it in this manner I have given here. That is half of norm of w square minus, summation alpha I yi w transpose xi plus b minus 1. And so the minimization problem is equivalent to constructing the, the Lagrangian function, and then obtaining, or solving, the Lagrangian dual problem actually. I have simply written the Lagrangian function actually. So what is that, so basically the Lagrangian dual problem will be, like this, that is maximization of minimization of LP of this, so here you have the variables w vector is unknown vector, w vector is coming, b is coming, alpha is coming. In the dual problem, we used to eliminate the primal variables, that is, w vector, and then, b, we are going to eliminate it. And the problem completely, we are going to bring it in terms of, the dual variables, or, the Lagrangian multipliers. So what is that, you take the derivative of, the Lagrangian function with respect to, the primal variables, w vector, and then b equal to 0. And you equate it, and then you solve it, you will get, w as unknown is equals summation of alpha and yi xi. And then, del LP by del B is equal to 0, it leads to summation alpha and yi is equal to 0. You see that, in order to find out, W, I have to compute the summation of I equal to 1 to m of alpha I y I x I. OA is in basically output value corresponding to the its value is either plus 1 or minus 1, depends upon what is your xi. So xi ka what is the output level you are associated, that I am going to replace it here as either plus 1 or minus 1. Xi vector is, so it's a vector now, and this particular vector has each vector has n components, and this particular vector is an input. So this is known to us, yi value is known to us, xi vector is also known to us. So in order to know w vector, I have to know what are the values of alpha 1, alpha 2, etc., alpha m. So that we have to obtain by solving this the dual problem. But you have one equality constant. I have summation of alpha y is equal to 2. So okay, so this the problem is now becoming the artificial problem of solving the first problem. Okay, so the Lagrangian dual problem is basically maximization problem. Since the initial problem is a minimization problem, when you go to the dual, it leads to a maximization problem. So maximize summation alpha I minus 1 by 2 summation alpha I alpha j y x I transpose summation alpha is greater than 0 and summation alpha y is equal to 0. Please see that what is the objective function? Objective function is the function which you are minimizing, you are maximizing it. Okay? What are the constraints? The constraints are alpha I greater than equal to 0 is one set of constraints. Summation of alpha y is equal to 0 is one constraint. Alpha 1 greater than equal to 0, alpha 2 greater than equal to 0, etc. Alpha m greater than equal to 0. So greater than equal to 0 has how many? There are m number of constraints, non-negative constraints we call it. And then one equality constant I have. What is the equality constant? The equality constant is summation alpha y is equal to 0. Yeah. So you have basically it is m plus 1 number of constraints, where m number of non-negative constraints, negativity constraints, one equality constraint. And if you can see that the objective function, that is the function which we are maximizing it, which is summation of alpha I minus 1 by 2 summation alpha I alpha j yi yj etc. xj. So you can see that this is the problem of problem in determining the values of alpha. Right? So you can see that the product alpha I, alpha j, so alpha 1, alpha 2, or alpha 1, alpha, if I and j are equal, then alpha suppose and equal to 1, suppose, then you have alpha 1 square is coming. And suppose I is 1 and j is 2, then alpha 1, alpha 2 term will be coming, and so on. So this is basically the unknown way. So because we have to find out what are the unknowns. The unknowns are alpha 1, alpha, etc., alpha m. So in this particular problem, the objective function which we are discussing it about has the terms are alpha 1 square is coming, alpha 1, alpha 2 is coming, alpha I, alpha j for some different values alpha is coming, alpha m square is coming. So basically it's the quadratic in terms of the variables, unknown variables, or the variables. In terms of the variables, it is basically it's a function of linear quadratic in terms of the variables. So the objective function is a quadratic function. So it's basically it's a quadratic optimization problem, or problem is a quadratic optimization problem. And you can see that in this particular case, you have xi vector transpose xj. So this is basically we know that it's a dot product of two vectors, and that particular one gives you a value, a number. So the expression is that ultimately going to give you a value. Okay. So just to keep it in mind that the objective function has with respect to the inputs, yi yj is a value is either plus 1 or minus 1. It will not be a much a problem. You have xi transpose xj is the term which is coming. So just to keep that in your mind, this we are going to later on when we are going to this important the contribution, that is xi transpose xj. So this particular the dot product we'll see that we are going to later on when we derive it for nonlinear case, we are going to replace it by some this is very handy. To say that basically. All right, now that's so the problem you can write it so basically the problem is maximize summation alpha I minus 1 by 2 summation alpha alpha j yxa subject to these constraints. Alpha is the Lagrangian multiplier. This particular problem is to be solved. You can write it as a minimization problem also, this particular problem, by replacing, I mean, the objective function with the minus of, uh, summation of alpha I minus of that, you can take it, and then, the problem can be brought as a minimization problem subject to the same constraints. And once, I mean, you solve this particular, I mean, optimization, quadratic optimization problem, QPP we call it, and which means that you find out alpha 1 except alpha n, then the W vector, but ultimately we are not interested in alpha, alpha 2, I mean, we need it because, I mean, that, I mean, I will be using it to find out ultimately my W vector, okay? And which is, I mean, coming in my definition of, the decision surface, or, I mean, the separating hyperplane. So to know the separating hyperplane, we need this W vector. Also, it is possible to determine it. I am not, going into that. The important property that many of these alphas are. So I will tell you, so many of the alphas are 0 means that if you go to the previous line, W vector is equal to summation of alpha in yi xi. So I have, I mean, a vector W vector. We are writing it as a summation where many of these alphas are zeros. It means whenever alphas are 0, then, those terms are not going to contribute. That's it. So, which means that, I mean, which means basically W vector, the unknown vector, ultimately when we are determining it, this is represented or written as, represented or written with only a few number of non-zero alpha values. Alpha is greater than equal to 0, so they are basically, which means that basically W vector is, determined by means of few number of positive alpha I values. So which means that we say that many of the alphas are 0, and therefore W vector is written as by means of few number of alpha i's, which means that W vector has a sparse representation. This is what the terminology we use. Sparsity means basically a lot of zeros. Basically, that is what it means. So W vector is written, which means equivalent. It means that W vector is determined by means of non-zero quantities, non-zero, entities. Okay. So the second thing is that, I mean, these whenever, okay, now you can see that, I mean, what is this alpha is, how many alphas are there? You have alpha 1 greater than equal to 0, alpha 2 greater than equal to 0. How many alphas are coming? There are m number of alphas are coming. Right? Okay. Now, the interesting thing is that come to, I mean, the picture. You see in this particular picture, I mean, for each particular this, input points are, I mean, we have subtle points and we have square points. And we already stated that, I mean, we have m number of input data points. And how many alphas the dual variables we are determining is alpha 1, alpha 2, etc. alpha m, which means that same number of, as the number of input points we have to, determine the alphas. So you have, I mean, suppose that, I mean, we associate to each of these, input points one alpha. So first, suppose x1 is 1 point, suppose a subtle point. A subtle point, which is, whenever suppose, I mean, any of that, I mean, suppose x1 is one input, first starting vector, input vector. Now, this could be either a subtle point or it should be a square point, because these are the two class of points we are taking. Okay. Assuming that this is a subtle point. Okay. Then subtle points are also, I have, further, I mean, I can characterize these 2 points, this particular subtle points. How? One is that the subtle points which are lying on, I mean, the parallel hyperplane, that is W transpose X plus B is equals to 1. The other subtle points which are not lying on this particular parallel hyperplane, W transpose X plus B is equal to 1. If suppose that x1 vector, I mean, input vector is lying on this particular, the parallel hyperplane W transpose X plus B is equal to 1, then the alpha corresponding to alpha 1. Okay, in this case alpha 1. Okay, because we are assuming that x1 is the first starting point. So the if corresponding the alpha is alpha 1, the alpha 1 value will be strictly greater than 0. And whenever the circle points are not lying on the parallel hyperplane W transpose X plus B is equal to 1 in this particular picture, okay, it means for this particular input points xi, subtle points, which are not lying on W transpose X plus B is equal to 1, then the alpha value corresponding to such subtle point will be 0. This one can, derive it, through optimization, theory actually. So I'm not deriving it, but I'm not deriving it. It's possible, but we are not going to too much into that side. As an important property, I'm just stating that whenever any input point, if you take it, whether it is going to be a circle point or whether it is going to be a square point in this example. Again, whether it is a subtle point or a square point, the point is input point is going to either lie on the parallel plane W transpose X equal to plus equals to 1. In the case of a square point, it is going to lie on W transpose X plus E equals to minus 1 or not. If it is lying on the input, the vector Xi is lying on the parallel planes, one of the parallel planes, then that particular point, the corresponding the alpha value corresponding to that input point will be strictly positive, which is not equal to 0. Whereas if the point is what I have chosen, if it does not lie on this parallel plane, then the alpha corresponding to this particular points is 0, which means the parallel, the hyperplanes, sorry, the middle plane, where which is what is the how the middle plane is, to determine that the middle plane, what is that, we have to know W vector and B. So the W vector is basically determined by either the circle points or square points which are lying on one of these particular parallel. Okay, the other points are not contributing. So these particular points are called support vectors. That is, subtle points which are lying on the parallel plane W transpose X plus B equal to 1. How many are there? There are two subtle points which are lying. So these two parallel points are called support vectors. In addition to that, a square point which is lying on the other parallel plane W transpose X plus B is equal to minus 1. This is also a support vector. So the W vector is determined by few number of support vectors. The remaining points, remaining subtle points, or the square points which do not lie on either W transpose X plus E equals to 1 or W transpose X plus B is equal to minus 1. Their alpha values will be 0, and therefore these points are non-support vectors. Okay. All right. Now come to our so our problem is solving the dual problem. And many of the alphas, they are the double variables. When they are going the alphas which are associated to the input points, all the input points corresponding to each of the input points, we are associating the double variables alpha is, and then we stated what is the meaning of support vectors. The vectors whose alpha values are strictly greater than 0 are support vectors. And we also seen that W vector, the unknown W vector is determined by means of only support vectors, and it has a sparse representation. These are some of the properties. This is the simplest model of SVM, and this model is called the hard module model. Now I will come to the SVM with the soft module model. I will go a little bit fast now. I think we have some idea what is going on. Now, in general, the linearly, when the two class of points are given, the previous discussion we are assuming that, it is possible that, the two classes of points have been separated by means of a linear hyperplane, no? Okay, by means of a hyperplane. Right? Now, uh, in this, uh, you know, uh, we are going to relax that, that the two class of points are not possible to separate them by means of a linear, hyperplane. So what is, but still we are interested in, a linear model. Still we have not gone to a non-linear model. We are interested in, in a linear model where we are also going to, consider the case of a non-linear separation problem. So we have two given class of points are given. One is square points, another is, circle points, and we can see that, from the picture we can see that these two class of points are not possible to separate them by means of a straight line in the picture, or by it's not possible to separate them by means of a linear hyperplane. But what actually, still, we are doing is that we are interested to find out, two parallel planes. Equations are W transpose x plus b equal to 1 and W transpose x plus b equal to minus 1, as in the previous case, where, some points of subtle points, we allow them to be placed on the wrong side of, the parallel plane W transpose x plus b is equal to 1. For example, there's the xj point. You can see that it has to lie on the, upper side of the parallel hyperplane W transpose x plus b is equal to 1, but it's lying on the other side. We allow it. And in this case, we associate to this particular point, xj, a penalty. What is the penalty? The penalty is the zeta j, and zeta is the distance between the point xj and to the parallel plane, the parallel plane W transpose x plus b is equal to 1. How far away on the wrong side, the point xj is placed. So that particular distance is, suppose I assume that the distance is zeta j. So what actually, we are going to do is that, similarly, for, the other parallel plane W transpose x plus b is equal to minus 1. We want that these two parallel planes to be as far away as possible. But in this particular case, the equations are determined, and therefore the distance is m, which is 2 upon length of, uh, the vector w. And we want it, in this case also we allow square points to lie wrongly placed on the other side of, the parallel hyperplane W transpose x plus b is equal to minus 1. And suppose that xj is the point, square point, which is lying on the wrong side, and its penalty, the associated penalty is zeta j. And see that, with respect to the middle, like in the previous case, we are going for the middle hyperplane. We are interested to find out that. Post equation is W transpose x plus b is equal to 0. But in the picture, you notice one thing is that, with respect to the middle plane, the xj point is on the right side. But we want that, the x, because if you look carefully, in the SVM formulation, what we did it in the previous case, xj point has to be, actually on the upper side of the parallel plane W transpose x plus b equal to 1, when it should not come here. That's why we associated with the penalty zeta j. But with respect to, the middle hyperplane, even though there is no, problem, at least, there is, it's only, with respect to this plane, if you take it, W transpose plus b is equal to 0, then with respect to that, it is on the upper side. Which, there's no, issue with that. Because our condition is basically the xj point should be on the upper side of the parallel plane, W transpose x plus b is equal to 1. So, okay, whereas, this, the square point, it is not only that, it is wrongly appearing on the other side of the parallel plane, W transpose x plus b equal to minus 1. It is also wrongly appearing on the, with respect to the middle plane also. We allow that, but as long as, the penalty associated to the point xj is with respect to the parallel plane w transpose x plus b is equal to -1. Okay, so that we have to keep it in mind. Actually. Okay, now with this particular, wherever I mean the points are like the subtle points which are already on the correct side or the parallel, I mean the point subtle point which is lying on the parallel, for example the subtle point which is lying on the parallel hyperplane w transpose x plus b is equal to 1. It is not wrongly placed. It is lying on the parallel plane. That is also okay. No penalty will be associated to this particular point. So similarly with respect to the square point, and with this particular kind of a setup, we measure I mean the distance between the margin, which is I mean 1 second like in the previous case, but we want that that I mean assuming that to each particular I mean xj point or xi point, we suppose that we have the penalty as zeta j or zeta I. For wrongly placed point, the zeta I is, or zeta j is strictly positive, whereas I mean already they are the points like these circle points which are correctly coming. Similarly, square points which are also correctly I mean appearing, the zeta I or zeta j corresponding to these points are 0. So this is what I mean we are formulating. So we compute this particular one. Now we not only that maximize the margin, but we compute this particular error, I mean with respect to x1 point, what is zeta 1 is the error. What is the penalty? With respect to x2 point, what is the penalty? Which is zeta 2. With respect to x3, what is the penalty? Which is zeta 3. So zeta 3 may be strictly positive or it may be 0. If it is equal to 0 means that it is rightly coming with respect to the parallel plane. If it is strictly positive, it means that I mean it is coming on the wrong side. Okay. So we wanted to I mean not only I mean minimize the or sorry, the maximize the margin, which is equivalently equivalent to minimizing I mean norm of w square 1 by 2 times norm of that, which is the first term here. Not only that, now plus you have a constant times of we are computing basically the sum of the penalties we are computing it. Okay. So this particular sum, very sorry, this particular sum, this particular sum of the error or some, these are penalties, some of the penalties, okay, or some of the errors. This particular sum also we wanted to minimize it. Okay, so we have as a minimization problem. Now the objective function has two terms. The first term is equivalent to maximizing the margin. Second term is equivalent to what actually we are doing it. Second term is basically minimizing, some of the errors of wrongly appearing points, the input appearing points. The constraints are W transpose xi plus b is greater than equals to 1 minus zeta I. Similarly, I mean W transpose x plus b is less than equal to minus 1 times zeta I. This one. So in these particular two things, I mean one can combine the constraints like the previous case. So the problem is basically solving the optimization problem, which is the minimization problem of half times norm w square plus c times summation zeta I. And what is the condition? Subject to the conditions is condition or constraints. yi w transpose xi plus b is greater than equal to 1 minus zeta I, well zeta is greater than equal to 0. So this is where so as I already stated, the first term corresponding to maximizing the margin of second term of the objective function corresponding to the summing of and then finding the minimum of the the errors. So this is the problem ultimately we are solving. And so far we have done only linear model. So we are assuming that in the first case we derived it for if zeta all the zeta is a 0, then your model reduces to the linearly separable case which we discussed it in the just a few minutes ago, about 10 minutes ago. Okay. So this particular problem is the more general one, but this particular problem is basically giving us a linear model. So ultimately, I mean this we have to solve, and this particular problem one can write it as a unconstrained optimization problem of this form. That is, half times some elimination of half times of normal W square plus C times. The error can be, computed as, like this, which is, 1 minus of y w plus x plus b, of this you take. It's nothing but basically maximum, finding the maximum of 0 comma 1 minus y times of w plus xi plus b, this particular one. So in artificial theory, or in SVM, okay, in SVM, the first term is basically, we call it as a regularization term, or sometimes people call it as a penalty. And the second is basically the error term actually. So basically, the second term we are calculating the summation of the errors. First term is basically, very often we are going to call it as a regularization term. And this particular function L we associate here not corresponding to Lagrangian, but L here in this particular case, basically it means that the loss function is the terminology used. Loss is the basically the error loss, basically, which is, uh, the error which, we are going to obtain, so that's, that particular one. And in our case, the error loss function is 1 minus y times of x, which is, maximization of 0 comma 1 minus y times of x. So in our case, your x is nothing but L transpose x plus b. And this particular function is called, that is maximization of 0 comma 1 minus yx. So this is what is called, hinge loss of SVM. Here, you are computing the error by this particular manner. Obviously, question will come. So why you will take, the error, in this particular manner. Only the distance, theta is nothing but how far it is away from, the parallel hyperplane, wrongly placed. And then we measure it as a error. And some people take it as, just to take y is theta, I take, you are taking, no, I will not take, I will take square of it. Which means that you are taking, the error, you are measuring it, how far it is away, and take the square of it, you are taking it. That is sometimes useful when you understand to solve a little bit a simpler problem actually. So there are many things like that. It goes as I stated that we have hinge loss is the one. We can have absolute loss, which means that instead of zeta I, you take absolute value of zeta I directly. You can take that, or you can take the zeta I square. You can take, and there is something also called nowadays pinball loss, and which also L of x y is equals to p times of 1 minus yx, and if one is, that is 1 minus y of x is yx is greater than 0. Otherwise, you have with a minus of 1 minus p times of 1 minus y. Very often y is p is taken as half normally. If you wanted to take it as a very simple model, but you can change it to different values. Very often p is towards the input and value is positive normally. It's also lies, in fact its lifespan is 0 to 1. So you can see that there are other variants like you can choose instead of norm of w square the mention. These are all how you compute the distance actually. So some people can make the distance as the regularization term instead of taking the square of norm of w square, which is again it's basically summation. So that instead of that you can take it as summation of norm of wi. You can take, for example, that's possible. Some people take it as like the next one, like unlike in equation 1, equation 2, like half of norm of w square plus b square also people may take. It's also possible. Okay. So and so on. Okay. So we do not have much time, so I will be directly going into the dual, and then I will just explain how you can go to non-linear model. So the problem, above problem, what is our problem? This is the problem, right? So that is the minimization of 1 by 2 times norm of W square plus C times of summation of zeta I subject to YA W transpose Xi plus B equal to 1 minus zeta I, where zeta is greater than equal to 0, where I is equal to 1 to M. So this is the problem, how you solve. You solve by introducing, you solve is doing consecutive dual, and then you solve it, like as in the previously, explained. So, the problem becomes maximize summation of alpha I minus summation of yi alpha alpha xi xi. You see that this is, the objective function is exactly same as in the previous case. There is no change at all. Huh? What is the change then? The constraints, in the previous time, we had only alpha I greater than equal to 0 and summation of alpha I yi equal to 0 only we had. But now we had another set of constraints, that is alpha I less than or equal to C. This is also has come. So basically we have, alpha I greater than equal to 0, alpha I less than or equal to 0. So this is, this constraint is, we call it as a box constraint. So it is a kind of, bounding the alpha values or restricting the value of, alpha is in, in from 0 to C, within a box, you allow them to vary within, a rectangular box in the case of 2D, 3D. But, in the general case, these constraints are called the box constraints. And so this particular problem, you will be solving. Otherwise, W is exactly same as in the previous case. You also have, the alpha i's, many of the alpha i's are going to be 0. And unlike in the previous case, the alpha i's which are wrongly placed, So for example, here. So we know that support vectors are not only the subtle points or square points which are lying on the parallel plane, W transpose X plus B equals to 1 or W transpose X plus C equals to -1. Not only these points, but the points, the subtle point, for example, xj, which is wrongly placed with respect to the parallel plane W transpose X plus B equal to 1, this point will be a support vector. It will also contribute in the definition of your W. And similarly, the xj point, which is also a support vector, and this is a point which is wrongly placed with respect to the parallel plane W transpose X plus B equal to -1. So this particular point will also now will become a support vector. So you have whenever the points are wrongly placed, they now also will come as support vectors, and therefore, the number of support vectors are increasing, which means that, the sparsity is reducing basically in a way. Okay. Now come to nonlinear. I will take only 5 minutes. Okay. So you have, in the case of nonlinear, the idea is that the input points, here, you take it into, yeah, in a very high dimensional space via some nonlinear function. So every particular point, you, suppose, I, through some magic, as if, I have your function phi. What the function phi does, maybe the input points are two-dimensional points, but the phi function, what it will take, the two-dimensional point, it will take it into some n, 10-dimensional points, maybe, for example. So every particular input two-dimensional points, I apply the phi value. Then I will get in, phi of x1, phi of x2 vector, phi of x3 vector, and etc. Each of these phi of x1 vector, phi of x2 vector, etc. They all lie in, suppose, 10-dimensional space instead of 2. Okay. So which means that it is lying in a higher dimensional space. But in the higher dimensional space, the 10-dimensional space, we assume that these points, after transforming, after, from the starting phase is the initial, input is given, the data point. Now, through some magic manner, assuming that, some function is known, via that, we have gone into a higher dimensional space, the nonlinear fashion. The nonlinear fashion takes these initial input points into, points in such a way that, after transforming, they become separable, linearly separable, which means that, it's possible to separate them by means of linear hyperplane in the higher dimensional feature space. So this assumption. So once I do that, it means that instead of now performing, my optimization problem, or, the whatever the theoretical study we carried out in the input space, instead of doing it, I will be doing it in the feature space. It's the hand and front, no problem. The feature space I will do, which means wherever, xi is there initially, now I will be replacing by phi of xi. And then, you go into the same kind of, the derivation. So ultimately, what you will get? So this is, for the linear case. So what is that? I have to do for the non-linear case. Wherever xi is there, replace it by phi of xi. So I have to solve in the case of, in the case of allowing some data points which are wrongly placed. For the nonlinear separable linear case model, I take the Artesian problem, and here instead of xi and xj wherever it comes, I replace by phi of xi and phi of xj. So I have, the Artesian problem becomes maximization summation of alpha I minus summation yi yj alpha I alpha j phi of xi transpose phi of xj. So this particular one is the only term I have to compute. I did not have to know explicitly even phi also. What I have to know is simply that, phi of x1 in dot product with, phi of x1, what is the dot product? Which is nothing but, it's the square of length of the square. Sorry, take the, square of the length. And then, phi of x1 dot product with phi of x2. So this dot product value only I know. There's no need that even phi I have to know explicitly. I have to simply know that what is, phi of x1, x1, phi of x1, x2, the dot product of these vectors only I have to know. Yeah? So the problem is now, I may not, in some way I am relieved that explicitly phi may not be, I may be needing it, but then I need the problem of, I have the problem of, how to compute phi of, x1, phi of x1 dot product of that, or phi of x1 and phi of x2 dot product of that, and so on. So that particular one, how to do that? So the case that, don't, since I do not know what is this phi business, so we will just, replace this particular via some kernel function. This is the important, contribution in SVM to move from linear model to nonlinear. So the instead of explicitly supplying or computing the phi of xj, the phi of xj dot product, the dot product is supposed, given via a function k function, which is a kernel function. Suppose that, we assume that, the kernel function is that, kya karo, you have to take x naught plus y plus 1, you take it, and then maybe power d is something, maybe for example, you can take the value of d could be, 1, 1.5, 2, 3, whatever that, depends on that. The popular, the kernel function is, applied in the literature of SVM is the Gaussian kernel function, which is defined as k of x transpose, k of x y is equals to phi transpose phi. What we are doing it? We are trying to replace the dot product of phi of xi and xj by via a kernel function. And so, the literature is, the popular, the popular kernel, the way is choose the kernel function as exponential of or e raised to the power minus length of the, x minus y vector you take, and the length is square of its length you take divided by 2 sigma square you take. Sigma is an input and it is positive. To change the sigma value, you have different, kernel values you are going to obtain it, and you can. So in order to go to the nonlinear model, what you have to do is that, you have to choose a kernel function first. And very often, when the Gaussian radial kernel function, which is given as k of x y is equal to exponential of or e power minus of, norm of x minus y square by 2 sigma square, that particular is taken. This is a popular, kernel function. And then, instead of phi of xi xj, you replace this particular, the kernel function. So this is what, we do. And then the problem is solved. And It is also, so this is ultimately, you have to solve it. And it is also possible to compute in this particular case, the nonlinear decision function. Okay. So the solution of the nonlinear decision function, you can see that now there is nowhere pi is coming actually. It is now summation alpha I k of x I x plus b. This is my decision function. There is a way how to compute b. I am not explaining it here at this particular point of time. And but b is also possible to via support vectors it's possible to compute it, and the distance function will be so with this I think I have been able to tell you that what is an SVM, how the SVM problem is derived, both for the linear model first we have derived it, and then the nonlinear model we have derived it. And along with this particular derivation, we have also discussed about, not discussed, I stated that what are the various, variants, like instead of taking this particular manner, the error function, you can change it to different, error loss functions. Or the regularization term, instead of using one type of a measure, you can take another type of a measure with some advantages. So that you have to go through the literature and then, you'll find it actually. And well, okay, so what is the algorithm? The algorithm is a choose a kernel function, choose when a C value, then solve the correct programming problem, and then construct once you have solved it, you'll find out what is alpha, and then alpha you have to use it to determine your W, which already I have given the formula. So you will just go into that, then you can find out the concentration function. You can easily find out the support vectors also. Okay, so with this, this is how you do. There are issues are there, like which particular kernel function I will choose, whether polynomial kernel function, Gaussian, or something different. And then after choosing this particular one, how do you choose this? Suppose I choose Gaussian. Yeah. I know. So suppose you have chosen a Gaussian kernel. How to choose the kernel sigma? How to choose the sigma? How to choose C value? So these things are some of the issues which which is coming. So these particular things are also there are ways of doing that. But my aim in goal in this particular my goal in this particular discussion is basically to give an impression to the how the linear. First of all, what is an SVM? In terms of a simple picture manner, and then how you can basically a linear model can be derived, and then ultimately how the nonlinear model is derived. So you now have an idea of what is it. Then you can now go for an application. So what is the advantages? Ultimately, better generation ability, which means the accuracy, power of accuracy is the result of accuracy is very good actually in terms of other methods. Kernel trick is where how you choose how you move from linear to non-linear case. Another problem is that when the data is of a very high dimension, the number of attributes are large, then there is a problem actually. This particular method, it will create some. This is a problem with everywhere actually. So that will be one issue which is also there.